In the previous lecture, we described unconstrained nonlinear optimization in the univariate case or when there was only one decision variable. In this lecture, we are going to see how this is extended to cases where there are multiple variables that act as decision variables in the optimization problem. So, when you look at these types of problems, a general function z could be some nonlinear function of decision variables x2 to x1 to xn. So, there are n variables that we could manipulate or choose to optimize this function z. A simple demonstration of this in a two dimensional case is root of x1 squared plus x2 squared. Notice that we could explain univariate optimization using pictures in two dimensions. That is because in the x direction we had the decision variable value and in the y direction we had the value of the function. So, you could see something like this and then say this is the minimum and so on. However, when you just extend this problem to two dimensions, then you have to have three dimensional plots, and in dimensions higher than 2, if the decision variables are more than 2, then it is difficult to visualize. So, what we are going to do is we are going to explain some of the main ideas in multivariate optimization through pictures such as the one that I have shown on the left side of the slide. And as I mentioned before, since even for cases where there are two decision variables, we need to go to 3 dimensions. That is simply because if this is x1 and this is x2 or this is x1 and this is x2, I need a third dimension to describe the value of the function x1 comma x2 equal to z. So, the objective function value becomes the third axis. So, let us look at how we think about this unconstrained optimization when there are multiple variables. Take this picture for example. So, if you look at this picture right here on the left hand side of the slide, you will notice that the minimum point is somewhere around here, which in this case happens to be 0 0. This is touching the xy x1 x2 plane and the solution minimum point is 0. Nonetheless, if you start moving in the x1 x2 plane, then when you compute the objective function at different points, let us say I compute the objective function at this point, then this is going to be outside the plane and this is the value of the objective function at this point. And if I compute the objective function at this point, it is going to be outside the plane, this is going to be the value of the objective function at this point and so on. And if I go this direction, I might come here and so on. So, what we are going to do is we are going to be in the space of decision variables and we are going to try and find an optimum solution, because those are the values that we are actually choosing. So, for example, if let us say I have a point here on the space of the decision variables, then the corresponding objective function value is this, and clearly we know that that is not the minimum point. So, what we need to do is we have to figure out somehow to get here. Notice that the point at which the decision variables take values such that the function is a minimum is also in the decision variable space. So, essentially when we keep changing the values for the decision variables, we are basically moving in this plane. However, while we are moving this plane, we are looking at the values in the z direction to find out whether the point that we have reached is a minimum or not. To better visualize this, we draw what are called contour plots, which I show on the right hand side of this picture. So, think about a plane that cuts this objective function plot parallel to the x1 x2 surface. So, for example, let us say you think of a plane like this which is parallel to this and it is going to cut the objective function plot. Now, if you have a plane that is parallel to the x1 x2 surface, then what we are going to see is we are going to have the objective function value be a constant across the plane, because when you project it here it is going to be at a particular f of x1 x2 value or z value. So, what one could say then is that if I cut this surface with a plane parallel to x1 x2 surface, then I am going to get what are called contours on the x1 x2 surface. So, you want to think about it this way. So, here is a plane that is cutting the surface. So, on the plane wherever the surface is cut, you are going to have a contour, and what we are going to do is we are going to project that contour onto this x1 x2 surface. So, that is the plot here. So, for example, we could take z equal to 5 and then have that plane cut this surface, then let us see what the projection of that in x1 x2 axis will be. So, we know that we are going to keep or hold the z equal to 5 as a constant. So, we will get this equation root of x1 squared plus x2 squared equal to 5, which will give you x1 squared plus x2 squared equal to 5 squared. So, this we all realize as equation of a circle centered at origin with a radius of 5. So, which is what you see in this plot. Similarly, if you say k equal to 4, you will get this contour plot, and k equal to 3, k equal to 2 and so on. Now, an interesting thing to notice is if I start with some decision variable values here, and let us say I want to improve my objective function, I know that if I pick a contour like this and then from here if I keep moving on this contour, I am not going to make any improvement to my objective function value. I also know that as I go away from this point in this direction, let us say I go to a new point, then that would be on a contour where the value of k is larger than where I was here. So, that means I have increased my objective function. So, if I move in any of these directions, I am going to increase my objective function. So, the one way in which I should move to decrease my objective function is to move in this direction, because however much I decide to move, if I let us say move here, then this is the contour. So, the objective function value on this contour is less than this contour. So, this point is a better point than this one. So, this is the basic idea about how we optimize this function. Now, as I speak, you would have noticed that there are two decisions that I need to make. The one decision that I need to make is, of all of these directions, what direction should I choose? So, I have to sit here and then make a choice about the direction that I need to figure out. And once I choose a particular direction, let us say I choose this direction, how far should I go in this direction is another decision I should make. So, for example, if I go here, I have made some improvement to my objective function. Let us say if I go here, I have made much more improvement to my objective function, but let us say if I go here, I have actually made my objective function worse. So, there are two important things that I need to decide. One is the direction in which I should move in the decision variable surface, and once I figure out which direction I should move in, how much should I move in that direction. So, those are two important questions that we need to answer. We will answer these questions when we look at numerical methods of solving these kinds of unconstrained optimization problems. In this lecture, what we are going to do is we are going to show you the analytical conditions for minimum in a multivariate problem. Before we do that, just like we saw in the univariate case, let us say this is f of x and then I have a function like this which has only one minimum, which is a global minimum, and then I also showed another case where we have a function maybe like this, where this is one minimum, this is one minimum, both are minima, this is a local minimum and this is a global minimum. This same thing happens in the multivariate case also. Here is an interesting example of a function where there are two decision variables, let us say x1 and x2, and the function is of this form. If you plot this in a 3D plot, you will get this. You can see there are many hills and valleys in this, and you will notice if we do the projection of this onto the x1 x2 surface, you will see that there are several minima in this picture, and you will see that the global minimum is here. So, you can see how hard it can become in case of functions like this, where if you let us say you start from here, then clearly one of the good things to do would be to go to this minimum, and you will be here, and from here when you look at the conditions for minimum, there will not be any difference between the conditions here and the conditions here in terms of the first order and second order conditions that we talked about. In the univariate case, we will see what the equivalent conditions are in the multivariate case subsequently. However, from just those conditions you will not see any difference. Nonetheless, if you actually compute the objective function value at this point and this point, this will be much smaller than this. However, when you are here, you have no reason to suspect that a point like this really exists unless you do considerable analysis. So, in cases like this, what you will have to do is you have to see whether you can improve it further. That basically means, though you know locally you are very good here, you have to do some sacrifice and then try and see whether there are other points which could be better. So, there are algorithms which will let you jump here, and then maybe you will jump here and so on, but these are all algorithms where it is very difficult in a general case to prove that I will go and hit the global minimum. Now, remember this is something important to note, particularly from a data science viewpoint, because let us say this is your error surface, just as a idea for you to think about how important these concepts are, and you are trying to fit a model, and the best parameters for the model are here, but a typical optimization algorithm would get stuck anywhere in any of these local optima. From a data science viewpoint, what it means is that the error is not as small as it could be here. However, from the model viewpoint, if you were to change the parameters from this value in any direction you change, you will be finding out that the error actually increases in the local region. So, there is very little incentive to improve your objective function value, very little incentive to move away from this point, because locally you are increasing your objective function value. So, ultimately your algorithm might find parameters which, while may be acceptable, are not the best. So, this is one problem that needs to be solved really to have good efficient data science algorithms. So, let us get back to finding out analytically how we solve this problem. So, if you have a multivariate optimization problem where you have z is f of x1, x2 all the way up to xn, and in the univariate case, let us just contrast this with the univariate case. So, let us say z equal to f of x, just one variable. Then remember, we said the necessary condition for a minimum is that I should have dz dx equal to f prime x equals 0, and then we said d squared z dx squared equal to f double prime x is greater than 0 for minimum. So, these are the conditions that we described in the previous lecture. So, the derivative in a single dimensional case becomes what we call as a gradient in the multivariate case. So, in this case we have dz dx or df dx. However, since there are many variables, we have many partial derivatives, and the gradient of the function f is a vector such that in each component I compute the derivative of the function with respect to the corresponding variable. So, for example, this is dou f dou x1 is the first component, dou f dou x2 is the second component, and dou f dou xn is the last component. So, this replaces this in the single variable case, and this is replaced by what we call as a Hessian matrix in the multivariate case. So, this is a matrix of dimension n by n. The first component is dou squared f dou x1 squared, the second component is dou squared f dou x1 dou x2 and so on, and you fill out the row like this. So, the notation that we have used is we have used the x1 in the front here and x2 here for second column, x3 here for third column and so on, xn here for the last column. Now, this is with respect to variable x1. Now, you can do the same thing with respect to variable x2. Notice here that x2 has come before x1 because it is in the second row, and this diagonal is always with respect to the same variable differentiated twice. So, this is dou squared f dou x2 squared, dou squared f dou xn square and so on. Also notice that this Hessian will be a symmetric matrix, because for most functions this equals this, and similarly you will have dou squared f dou x1 dou x3, the next term here will be dou squared f dou x3 dou x1, which will be the same. So, the Hessian matrix is going to be symmetric. Remember, in the linear algebra lecture we said that we will be seeing symmetric matrices quite a bit, and here is a symmetric matrix that is of importance from an optimization viewpoint. Now, what we need to do is we need to see how these conditions in the univariate case translate to the multivariate case. So, much like what we did in the univariate case, we are going to do a Taylor series approximation, and what I have done here is I have just written it till 2 terms. There are more terms here, but what we are going to do is we are going to make the argument that if you make the distance between the point that you are at and the next point that you are going to choose very small, then whatever is the leading term in the sum is going to decide the sign of the whole sum. So, in other words, if you take this whole thing right here, if you keep making this as small as possible or as small as needed, then what will happen is the fact that whether this infinite sum is positive or negative can be identified only by the first term, and if that is positive, then the whole sum series sum is going to be positive and so on. So, that is the kind of the logic that we are going to use again here. Much like before, we said that if I keep making this small, I need to only look at this here, and much like the univariate case, if this does not go to 0, I can make this term either positive or negative. To see this, if I take a particular direction and then say delta f transpose alpha, if this turns out to be negative, this number, then if I go in the opposite direction of minus alpha, I will get grad of alpha, this will be positive. That means that I will have a point here which can be either larger than this or smaller than this, and if I can find a point such that this is smaller than this, then this cannot be a minimum. So, whatever you do, unless this goes to 0, I cannot ensure that this is a minimum point. So, the first condition that we will get is that this is 0, and once that is 0, then I am left with just this term right here, and if you notice, this term is of the form delta transpose the Hessian matrix, let me use H here, delta. We know that this is a symmetric matrix, and let us also make sure we understand this clearly. The function f is a scalar function, and you can see that here also H is an n by n matrix, lambda transpose will be 1 by n and lambda will be n by 1. So, when I do this, I will get 1 by 1, which is a scalar. Now, irrespective of this x bar, if this is a positive number, then we can say irrespective of whatever direction you take, this will always be greater than this in the local region, which would qualify this point x star as a minimum point. So, that is an important idea that you should remember. So, we come back to this. In the last slide I wrote this as delta transpose H delta greater than 0, H is symmetric, H is basically this second derivative matrix. Now, we did not see this in the linear algebra lectures, but if I need this condition to be satisfied irrespective of whatever delta is, then we call this H as a positive definite matrix. So, if H is positive definite, then this will be greater than 0 for all delta not equal to 0. Clearly, when delta equal to 0, this will be equal to 0. So, how do I check if a matrix that I compute is positive definite or not? Remember from the linear algebra lecture, we said if I have a symmetric matrix, then I will have the eigenvalues as being real. So, symmetric matrices always have real eigenvalues, and the eigenvalues could be positive or negative in this case. Now, the linear algebraic result for positive definite matrix is that if this matrix has, let us say, n eigenvalues, and if all of these eigenvalues are greater than 0, then this matrix is called positive definite. In other words, if all the eigenvalues of this matrix are greater than 0, it is automatically guaranteed that whenever we compute this for any delta direction, we will always get a positive quantity. So, this has already been proved. So, if you want this to be positive for any direction, why do we want this? We want this because we want f of x star to be the lowest value in its neighborhood, and that we said will happen if this is positive for any delta, or for every delta this should be positive. That condition can be translated to H being positive definite, and H being positive definite can be translated to the condition that lambda 1 to lambda n, the n eigenvalues of H are strictly greater than 0. Now, what this does is the following. So, in a multivariate case, it gives us a way to identify points that could be optimum points, and once we identify those points, we can compute this Hessian matrix at those points, and then computation of the eigenvalues of this Hessian matrix would allow us to determine whether the point is a maximum point or a minimum point and so on. So, this is the complete equivalent of what we did in the univariate case. So, to summarize, in the univariate case, the two conditions are f prime has to be 0 and f double prime has to be greater than 0. In the multivariate case, these translate to grad f equal to 0 and the Hessian matrix being positive definite. Let us take a very simple example and identify an optimum solution. So, consider this multivariate example. So, there are two decision variables and this is a function in terms of these two decision variables. So, what you can do is you can first construct this grad f vector, which is dou f dou x1. So, that would be dou x1 will be 1, this will be a 0 term, this will be 4 times 2 times x1 8 x1, this would be minus x2 and this would be 0. So, the first term is dou f dou x1 here. Similarly, when you do dou f dou x2, I will have a term corresponding to this 2. This when differentiated with respect to x2 will go to 0. Corresponding to this, I will have a minus x1 now, and corresponding to this I will have 4x2, which is what we have here. So, we have these two equations that we need to solve. So, when we solve this and get let us say one of the solutions x1 star, x2 star is this here, I can check whether this is a maximum point or a minimum point. To do that, what I have to do is I have to do this second derivative matrix. So, the way you do the second derivative matrix is the following. So, the first term is dou squared f dou x1 squared. So, we already have dou f dou x1. So, if you differentiate it with respect to x1, you will get this term. So, the only term remaining will be 8, which is what we see here. And when we look at this, we already have dou f dou x2. So, we have to differentiate this with respect to x1. So, the only term remaining will be minus 1, which will be here, and I already told you this is a symmetric matrix. So, you can simply fill in the minus 1 here, and to get this term I already have dou f dou x2 here. I differentiate this again with respect to x2. So, the only thing that will be remaining would be 4, which is here. So, I have this. Now, what I need to do is I need to compute the eigenvalues for this, and when I compute the eigenvalues for this, I find the eigenvalues to be both positive. That means that this is a minimum point. Now, when we look at this equation here, there are two equations in two variables and both are linear equations. So, there is going to be only one solution here, and it turns out that that solution is a minimum for this function. So, this finishes our lecture on multivariate optimization in the unconstrained case. What we will do in the lectures that follow, we will look at some numerical methods for solving these types of problems. We will introduce the notions of how to solve these problems when there are constraints. We will look at two types of constraints. One are what we call as equality constraints. The other type of constraints are inequality constraints. So, we will pick up from here in the next lecture. Thank you.